And now, after all that meeting information, I'm proud to give the stage to Professor Steve Shaw. Steve, please.
It's a real pleasure. I wish I could be there. I have very strong memories of Kompedal and Lyngby and just all of Zealand. So I hope someday we'll actually get a chance to see each other. Just to sort of give it an introduction, I'd like to keep this very informal. So I know we can't have the direct interaction or interruptions, but any comments or questions or complaints you might have, just put them in the chat and we'll get to them. The main thing that we'll talk about is something that comes from probably the most important single observation that Tycho Brahe made in realizing that the comet of 1577 didn't show any observable parallax and yet moved in the sky, and the Stella Nova of 1572 showed no parallax and didn't move in the sky, that one of them, comets, were a very well-known phenomenon. They were usually classed in meteorology in Aristotelian sense, that they were either classified according to their form and displacement, or that somehow they were connected with the transients that occur in the atmosphere. They were always considered sublunary. There was one class, so I'd just like to put this in some historical perspective, because it did, after all, in large part begin on Wien. And in the period from about 1572 to roughly 1620, the realization that there really were stellar components of the universe, things that lived in the sphere of the fixed stars that weren't bloody fixed, that they actually changed over time, and yet were clearly beyond the parallax of the moon, and so they couldn't possibly be meteorological. This is from a 16th century manuscript at the Bibliothèque Nationale, and I chose it for a particular reason that you can't quite easily see it, but Ptolemy, who always gets the publicity in these manuscripts, is pointing to something in the sky that you might think is a cloud or something like that. It's actually one of his classes of comets. In the classification of comets that was current at the end of the 14th and early 15th centuries, the classification into 9 categories included a group that had no tails, of which one, Rosa, was described as holding its place for a long time. Now, this may very well be the first indication that somehow European observers recognized that there was some extraordinary class that might actually be in the sphere of the fixed stars that would be cometary in nature, but otherwise perhaps superlunary. But by the beginning of the 17th century, it was pretty damn clear that there were objects that actually changed in the sky. Few of them were sufficiently bright that just about anybody would notice them, especially somebody who wanted to make a killing on astrological predictions. And as the astronomical interest of the philosophically minded community turned again to natural phenomena, that is, turned back to the sky, to the earth, to living things, to physical processes, instead of just burying their nose in books, the rate of discovery of things that varied in the sky steadily increased. And specifically, although we have virtually no unambiguous references to variable stars or to novae or supernovae in the Western literature before the beginning of the Renaissance. After that, and especially after the invention of the telescope, the telescope and the astronomical telescope, there was an explosion of interest in the sky, and consequently a recognition of things that were changing. I'll just mention this because all of you are interested in just observing that the essential feature of the nova phenomenon or of supernovae is that it's transient. And something that came up in laboratory with my students a couple of weeks ago when I was discussing large-scale surveys was one of them asking how you can predict transients, which is, if you think about it, one of the things that makes them so interesting. They're not predictable, or at any rate, not the first time. It's very difficult to say what particular system is going to go in tilt. And that's also what makes the study of objects like novae somewhat different than the study of supernovae, but we'll get to that. I just thought I'd throw up a couple of slides here to kind of explain things. The top slide, top left, is the rate of discovery from the beginning of the 19th century. It's a linear scale in time and in number, but you see that there were two breaks here. Now, both of these are from your community. The first group is those who were just noting the brightest novae in the period when visual observations were about the only way to do this. Then at the beginning of the 20th century, after the Carte du Ciel and some of the attempts at doing all sky surveys, but especially with the so-called selected areas studies, which were designed to do galactic structure. They were not designed to look for variable objects, but they were photographic. And so once an area was observed, it could be reobserved and compared instead of relying on human memory or anecdote or published reports. An observer would be able to directly compare something with an archival observation. And there was an order of magnitude jump in the rate of discovery. That pretty much flattened out until about the beginning of the post-war period, when the Palomar Sky Survey produced an all-sky, well, all northern sky, so we're hemispherically racist here, but a record of the sky in the period between 1948 and about 1950 that covered the sky completely down to about 22nd, 23rd magnitude in two colors. In other words, you had a photographic record of the sky, again, relative to which any field could be compared. So if you had an object that you observed as a transient, you could go back and say something about what it might have been before the outburst. The next jump, this enormous jump that hasn't ended, is the combination of CCDs, electronic processing of the data, the invention of the FITS file, which allowed for the exchange of data and a standardization. And most importantly, in the last 10 years, the introduction of networks of robotic telescopes that in the last 5 years have proven to be the most productive on transients, because since they monitor the sky in a set pattern, they can keep returning to the same place and recognize what's going on if they're scanning. There are others like OGLE that just sit and look at one portion of sky, like the galactic center, and just keep monitoring the same area. So signaling the existence of a transient is extremely easy. The bottom left is the magnitude at the time of the outburst. And while this tail of the brighter ones above, say, 5th or 6th magnitude is what is mostly populated by this period before 1900, this peak at around 10th magnitude is actually quite important. That once you get sufficient statistics in this modern period, you find that there's a characteristic of the nova outburst that's different from just about any other transient we see. It has a certain energetics, and more to the point, when you talk about something that has a range in brightness, but has a very well-defined peak, and this is not something that's just an artifact of the observations. It's not just a selection effect. Then that's because of the distribution of the object in space. That we have a pretty uniform population of these things that also has a characteristic rise from minimum. Again, this is in magnitudes, but these stars not only peak at like 12th magnitude at time of outburst discovery, but having an amplitude that's about 12th magnitude makes it relatively straightforward to follow these even back down to quiescence. And now in this piece of the modern era means you can go backward if that area was surveyed with CCDs. It's very likely that you'll be able to find the progenitor. You'll be able to study the system by literally going backwards in time and understanding something about where it came from. Now, we couldn't do that, say, 10 years ago. One of the most remarkable possibilities that we have now with the wealth of data that's been accumulated just by random pointings in the sky, but also with new instruments that are coming online, like the Large Synoptic Survey Telescope, there's a possibility that we're going to be able to have a very large number of candidates that will allow us to go backward in time instead of forward. But I'll try to get to that in a little while. For those who are used to photometry, this is the panoply of extrema that novae come in all varieties, okay? That turns out to be far less important as an indicator of what the explosion was than we used to think. And Novae 2013, Nova Centauri in the same year, and many of the recent novae have finally allowed us to understand what's going on here among these different light curves, and that this is actually something that's hiding much of the information about the underlying object. But again, I'll come back to that. There are classes that seem to just go sick. You know, they have an outburst, they kind of bop around for months, and then suddenly they decide they're going to form dust, and they go through deep minima. This is perhaps 10% or so of most novae. A lot of them just look dreadfully boring when it comes to photometry. They have a spike and they just decay, almost as if they were single events, like a switch turned on, and then it just discharges. And then there are the others that show some structure at peak, but basically, this is the pretty much normal nova. This would be called fast. This would be called, well, I can't say it because it would be uncivil, but this would be the sort of nova that would attract more attention. And actually, this is one that is currently attracting attention. Not this particular, but Nova Persei that had an outburst at the end of 2020 is actually of this type. There's another thing, which is, I think, shown best here, that novae actually recur. This part is wishful thinking. That is, this is a logarithmic scale. So we're here at 10 years and a century and so on. To say that something recurs when you're talking about transients implies that somebody has a memory of it. And in this case, when talking about so-called recurrence times for Novae, there are really very few for which we have definite demonstration that these things actually are recurrent. That is, within living memory or within the last couple of 100 years, there's been at least a second outburst, a second explosion. So this business of putting a large number above 10,000 years as a recurrence time is largely based on a model and not an observation. But there are a couple of dozen that have recurrence times as short as a year. We didn't know that 2 years ago. There's a whole class that's emerging from observations of Andromeda, large and small Magellanic Clouds, M81, that because these are whole galaxies that are being monitored, have actually demonstrated that there's this class of extremely fast recurrence that are novae. So ultimately, well, okay, I'll leave that one aside. The key point is to get to the bottom line. A nova is an explosive event. It's one in which you have mass accreting in a binary system onto an object that must be degenerate. What I mean by that is a white dwarf. It can't be a neutron star because the temperatures of the accreted material, the compression that it would undergo as it settled onto the object would be far too high and not, in fact, possible under stable conditions. The rate at which we see material exchanged between the stars that form a nova system is just too bloody large to dump onto something that's like a neutron star. It would heat up and blow off immediately. Instead, what we know about these systems, let me just show you one observation that'll, I hope, warm your hearts. This is what photometry looked like in the 1950s. It was a chart recorder with a pen that was oscillating up and down. But this one particular observation is the beginning of everything that we know about novae. Everything that I've been talking about before that, I could have said 100 years ago. But this observation in 1954 of a nova that formed dust, we know that now, was one of the brightest novae of the 20th century and was beautifully placed for observations in the Northern Hemisphere. Nova DQ Hercules, 1934, was bright enough and had within this amplitude a large enough, started from faint, from not too faint for this epoch. Let me say it differently. The nova at discovery was not only naked eye, but it was really bright. If you take the amplitude that's typical, you find that it was possible in the 1950s with a large enough telescope like Lick to do with a 1p21 photomultiplier photometry of a system that might be left over after the explosion. DQ had already been identified as a very bright blue object, we would say very bright now, in the center of a small nebula. So it was known that this was the remnant of the system. Walker started doing photometry of this thing, and within one season had not only determined that it was an eclipsing binary, that the period was less than a couple of hours, and that there was also an oscillation imposed on this thing of 1 minute, but also that the eclipse was virtually total and lasted only a matter of minutes from ingress to egress. That was remarkable. That indicated that the system had to be a compact object with a normal companion, and identified the companion as a white dwarf. So once by the mid 1950s, once that was known, within 10 years, the model was fixed. We knew that all of these systems that had compact objects, these bright blue white dwarfs, also corresponded to the dwarf novae, and all fell into a category that are now called cataclysmic variables. But this particular one and others like it have been found as the remnants of systems that went through an explosive event. So to put it in perspective, this was dinner a few years ago, but it was also the best model I've been able to find to show you of what a Novae system actually looks like. But let me explain something a little bit better here with some cartoons, okay? So here. I hope you can see the whiteboard here.
You can.
Okay, so in the course of evolution, you know that stars process their nuclear fuel, and you have the conversion of light, systematic of light to heavy elements, ending with the metals of the iron group. That part's not as important as the end product isn't as important as the fact that there's nucleosynthesis going on in stars. So it's an irreversible process. The core gradually converts, that is, any part of the star that's sufficiently hot and sufficiently dense to undergo thermonuclear reactions will. And this will continue until whatever can react is no longer available. So if you start out with a star that has a composition like the sun, over time, the core will convert from helium and may actually, not if it's a solar mass, but a little bit more massive, it will wind up in the range of carbon or oxygen in the core. And the core will be very dense, but in the same time, the radius of the star is going to slowly increase as it's going through hydrogen core burning. But if this interval is, say, a few billion years or a billion years, in a very short time compared to that, something like a few percent, the star goes from a core that's burning to one that's rapidly contracting as it loses energy. And that heats up the envelope and causes it to expand. There's nothing very special about this. You know, think of it this way, that if you start out with a star that's homogeneous and it starts building up a core and then you turn the core off, this thing is hot. This part isn't. So you're going to be losing energy. The outer part, as you know, because you observe stars, the outer part is just free space. So ultimately, if you don't supply the energy, the star is going to cool. It has no choice, and it's going to cool radiatively. So there's going to be a diffusion of energy from the core outward. Now, the core is supported by its own pressure against gravity. And so if this starts to cool because it has no nuclear source, it's still going to be releasing energy that heats the rest of the star. And since this part doesn't have the whole damn star on top of it, it can expand. So very rapidly in this last stage, as it approaches a red giant, the radius goes from a few times that of the sun to perhaps 100 or more times its original value. And it does that on the approach to the red giant. Okay, that's if the star is just sitting on its own. Okay, it's gone into quarantine because of a galactic pandemic, and nothing is constraining its expansion. The problem is a little bit different, as you may know, if you have housemates or cohabiting in your apartment, that you can't just take your junk and expand infinitely into everybody else's space. Sooner or later, somebody is going to get annoyed because you're starting to dump material on them. And that's exactly what happens here. That if you've got two stars that happen to have different mass, and they're separated from each other in orbiting, the center of mass in this case is, say, over here. As this star evolves, it's going to be aging effectively more rapidly than a lower mass companion. This is inevitable because the rate of nuclear reactions depends on the temperature of the core, which depends on the compression, and that ultimately depends on the mass. So this star this star is expanding while this one is expanding much more slowly. And it's possible, if these two were close enough together, that one of these stars will literally overrun the other and form what, as far as the world outside would be concerned, is something that looks kind of like a common envelope. That is not like a contact system. This is much more dynamical, that all of this is going to be turbulent and circulating, and this poor cohabitant is going to be buried inside this envelope. But at the same time, it's moving in this envelope. And so it's providing energy and heating and losing energy from its orbital motion. So what you're going to wind up with at the end may be this star stripped down to its core, with a companion now that's close, so close, in fact, that the orbital period between these two may be only a matter of hours, where here the orbital period may have been initially closer to months. So you wind up with nothing left of the star that first went through this common envelope phase, except the stripped core, and that's a white dwarf. If the mass range is right, the dwarf is going to have either a helium or a carbon or an oxygen-rich composition. It depends on how far nuclear processing got before these stars decided they were going to do something unpleasant to each other. Okay, now the story doesn't end here. Once you've got this compact system, you still have this other character evolving. It hasn't stopped. It may have been damaged, but it's not dead yet. On the other hand, this one is. There's nothing happening on the dwarf. So if we blow this system, if we expand this system, then we also see that there's a tidal limit to how far one of these stars can expand before the differential force from this companion has so distorted it that matter becomes unbound. Now, this part is the most important part of our story, that this star, the companion, and by now this is a very low mass object, that it must be, I can't say, but that it is, observationally, is certain. These are all much less than 1 solar mass. But where here you have an attraction from the white dwarf, you've got to remember that this is very much like turning on a faucet. in a sink. Okay? You open the faucet, and on one side there's nothing, and on the other side there's the pressure in the pipe. This is a star. So on one side there's nothing, okay? And on the other side there's a star. In other words, this thing is literally overpressured relative to the background, and material is necessarily going to be forced out of this star. That it's forced out in the form of a stream is the particulars of the way the force exerted by the companion white dwarf distorts this object. But because the system is orbiting, this material doesn't fall straight to the white dwarf. It circulates, collides with itself, and eventually forms a disk. That is what sets up the nova. That this material, lost from the companion, isn't lost from the system. It's starting very close to rest. In fact, I think the closest example you could have in your experience is if you take a faucet, so, okay, if you just do something like this, open this, put a tube on it, and then here, have a drain, okay? And if you do it right, you're going to get the formation of a disc here, which will initially circulate and gradually fill out and give you a steady state flow down the hole. And you can play with the angle that you want here, but the material is drifting in because the disc, the water, has a viscosity. It's losing energy because of internal friction. And if you think of the whole as being the equivalent of a gravitational source, and you realize that there's a limit to how much material you can pile on in this disk, eventually that stuff is going to drift in and drop down the hole. Now put a white dwarf on the other end, essentially a garbage bin, and this material starts to accumulate on the white dwarf. The star is immersed in this disk. The disk completely covers the surface of the white dwarf. And as this stuff piles on, coming from the companion, which was already just solar composition, something rather dramatic happens. In the compression, the temperature goes up. That's hardly special, except this is deep in the envelope. Eventually, you can accumulate a couple of planetary masses of material here, and that starts to get interesting because it's opaque. You can't get rid of the energy. It compresses, it heats up. It can't stay isothermal. And because of that, and because of the enormous gravity on the white dwarf, it's 4 orders of magnitude higher than the gravity on the sun. The pressures that this reaches on the surface of the white dwarf are the same as in the interior of the sun. Okay? That implies that at some point when enough of this material has accumulated, it is going to start thermonuclear processing. Now, it's not something that starts instantaneously, so don't get the idea that somebody flicks a match and boom, everything goes. But it does happen very, very quickly. And actually, I can show you an example of that, at least as far as a calculation goes. But let me just show you one other thing. So I hope you can see this sphere. This is a piece of Italy in Carrara, which is best known for its marble production. But a couple of years ago, just walking through town, I happened to see this fountain, and like being in a dessert, I was seeing a dessert that looked like a binary system. This looked like an accreting white dwarf, like this. You see the way here, the water is riding up on the surface of this rotating object. That's essentially the way that the material is going to spread. Okay? So you can think of this as a white dwarf inside an accretion disk, spreading this material. This is actually something like what the accretion process will look like. This is just next to my house. This is the Arno River. The free stream that you would consider the disk is out here. The white dwarf is on the right side, and this is the mixing layer between the two of them. Okay, so you've got this stuff falling on, shearing because it's on the inside of the disk, mixing into the interior. And perhaps some of you know that what happens in a carburetor in a car, it's the same thing here. You're pre-mixing this stuff, and at the same time getting it ready to flash. And when it does, it flashes under conditions that are extremely, extremely different than what happens in a normal nuclear process in a star. The background material is so dense that it's degenerate, which means it no longer behaves like a gas that knows about temperature. The pressure is only from the density. So you start releasing energy. The gas heats up. The electrons are supporting the medium. And I hope I'm not getting too technical here, but this is a plasma, so it's completely protons and electrons. There are no neutral atoms here. The protons, being so much heavier, are carrying the bulk of the thermal energy, and the electrons are providing the support by this degeneracy. But the point is, it's the protons that are going to be involved in nuclear reactions. So you can think of this as two fluids, one that's reacting like in a chemical lab, and the other that's just providing the box in which the reaction is taking place. The box doesn't react, so the temperature keeps going up. This is deep, so the energy can't be transferred radiatively quickly enough. So as the temperature goes up, without changing the density, the nuclear processing goes faster, and the material becomes unstable to boiling, literally to convection. Now, we don't see this. We can't see this. This is deep inside the envelope of the white dwarf. But we can at least calculate it because we know something about nuclear physics and something about the behavior of matter under these conditions. So I'll just show you a piece here of a calculation that we did. This is not the most recent version of it, but this is several hundred seconds into the beginning of this nuclear runaway, where the white dwarf is down here, and we're using a tracer. So this, you could think of this as a pollutant. I think you've seen things like this in investigative reporting of industrial waste, that this is a couple of 100 kilometers thick. Up here, there's the layer of the accreted material. Down here, there's the white dwarf. And this layer is where the reaction's initiated. And this is what it looks like, following only for a few, literally 100 seconds. Every change in color is mixing or nuclear reactions. And you see that there are bursts that can last matters of seconds. This on a scale of hundreds of kilometers. Okay? Now, The closest thing I can show you as a comparison, again, Italian experience is this. Okay, what the hell? Let me play it. Okay, that's a quiet day in a pizzeria,
Yeah.
pre-pandemic. But you see what's going on here. This is the interior of the white dwarf. There's the overlying layer. There's the white dwarf. This is the burning zone. This is convecting precisely because it can't radiate anything. And the conduction is so inefficient that the temperature just keeps rising here. Fortunately, most pizzerias don't go nuclear, but you know, some of them might. And well, if they did, we'd be able to see them as Novae, okay? But it's the same process. This in the nuclear sense is referred to as a deflagration. You know it as a forest fire. And post-pandemic, or if you do an order out, this is what you're going to be doing. Just make this material neon and oxygen and carbon, and instead of wood burning, make this a nuclear reaction. And there's absolutely no difference between them except scale. That's one of the reasons we actually understand what sets up the nova. If it weren't for the process being essentially classical, we'd have a real problem. This is much easier than supernovae, precisely because it blows up. It's not something that collapses and self-powers. This is literally a nuclear explosion under a layer in the surface of a white dwarf. It occurs to me that there's actually an example which is sort of terrifying, but you all know it from the news earlier this year, when in Beirut there was the explosion of the warehouse that was filmed from several different directions, where you could see the fireball from the explosion site. That is about as close to a nova as anything that you ever want to see in your lives. That is, you have material that was accumulating, gradually going through a chemical reaction that built up the temperature and pressure to the point where it became unstable and was simply triggered to an explosion by a spark or some perturbation. When I showed you this nuclear calculation that we did, the initiation of this was literally a spark. In an area of a couple of 100 kilometers, we put in the equivalent of a 3-degree Kelvin perturbation at one point, and then just let it evolve. And within a couple of 100 seconds, we had the beginnings of a runaway nuclear reaction. The same thing happened in Beirut. It simply happened because of a chemical. Okay? Now, at the nuclear explosion level, and therefore nova, this is what you see as a nova. The expansion first of the fireball, and then the fireball reaching a temperature and size at which it suddenly becomes transparent. Now, everything we understand about novae is connected with what we see from the outside. So we haven't seen anything in this first period, which goes for matters of minutes. The longest time to build up to an actual explosion is something of order 10 minutes. The explosion then fragments, and underlying this is this. This is, again, very close to what you see in a real nova, but this is fireworks, something you're all familiar with. Each one of these fragments came from a point source, and the actual explosive was probably about this big, maybe smaller. In explosion, this entire container literally disintegrated probably in a matter of a millisecond. But in doing that, unless you have somebody who's really skillful at shaping the charge in this box, if this just blows up, it'll do it ballistically. Every piece is going to fly off, but it's not going to have the same velocity. It'll be a range. That which came out with the highest velocity goes farthest. And the majority of the fragments aren't going to make it out very far. They're going to come out at relatively low velocity. This is characteristic of all explosions, but some of them are going to be going extremely fast. And this gives a characteristic density distribution, that high velocity material is rare and occupies a big volume, and lower velocity material is more abundant and occupies a smaller density high at low velocity, density low at high velocity. And as this stuff is expanding, it's becoming transparent faster than this is. That's it. That's a nova. Okay? That what you see initially is when this stuff is opaque, and then when this turns optically thin, essentially transparent, you start seeing progressively deeper. This stuff's hotter than this was. It's cooled. That's why it turned transparent. And so over time, you go from maximum brightness to a kind of decay. And eventually, this too will disappear. Okay? Now, this is if it's fireworks. There's one kicker here. Sitting inside this bugger, there's a light source. This didn't destroy the white dwarf. And that was the singular result of that discovery of the eclipses of DQ Hercules by Walker. The white dwarf was still there. First, that there is a white dwarf was identified by the timing and phenomenology of the photometry, but that it was the same object that had blown up, that it wasn't destroyed, was the key to everything I've just talked about. That once the explosion has taken place, the binary system remains. This is not like core collapse supernovae or supernovae type 1a. What is left over can do this again, but at the same time, it has to relax. Put it a different way, you can't do this kind of violence to a white dwarf and expect that it's just going to quietly go into retirement. You've heated the envelope of this thing up to a couple of tens of millions of degrees. It doesn't just say, okay, that's it, it's over, I'm going to go back to being a white dwarf. You have this outer envelope that's been completely restructured by this explosion. And it's going to take time for that to relax. In fact, it may never get back to its original state, because in the same interval, you've got material coming from the companion that's dumping onto this and blowing off because it's being heated and compressed. We don't know what happens in that immediate post-explosion stage. That's actually the biggest gap in what we understand about this. We know how it builds up. We know what happens in the long run. We have no idea how this thing relaxes in a couple of years after the explosion. I say a couple of years for this reason. So let me change screens for a moment. And so here, go back to cartoons. I really hope this is making sense to you all.
It's very, very interesting, and I think it's very good explained to us. So
well,
it's great. Let's continue for 5 more minutes and then take a short break.
Okay, so we'll get to
Yeah,
Okay.
this is great. So
Okay, so what we've got here is actually the easiest one because you're Danish. I mean, you know, there's this thing called the sea. You know all about fogs. And so let's say you're on the Oresund and it's a really bad day and you've got a lighthouse, okay, that's illuminating a fog, okay, and you're sitting out here. Now, as the fog lifts, you're going to see progressively more of the lighthouse, but you're still going to see something that's kind of diffuse, okay? But the lighthouse is still there. And eventually, you'll see something that might be the region that's foggy. In fact, it might even be bigger than you are. So you may be in here and you're going to see the white dwarf and you're going to see everything around it. In effect, this is what you're seeing in a nova. That if we just took here a piece of the expanding ejecta and we imagine that we're sitting out here and this is just a section, then the central object in here is heating the inner portion here, controlling the temperature and density structure of the ejecta. And so showing up here as a shell. Okay. And let me go get that.
no problem.
And we'll take a break, right?
Yeah, let's take a break. Kim?
Yes, thank you. And thanks a lot to you, Steve, taking the time to take us by the hand into
Not
all
at
these
all.
fascinating details. I was wondering is it possible to make a table of 3 columns? In the first one, your story of what goes on in each stage of the nova, and in the next column, what would we measure in photometry, multiple colors? What would be the corresponding light curves? And in the third column, a low resolution or medium resolution spectrogram for each of all those stages that you just described to us.
Actually, yeah. In fact, here, let's do it. So this should be the right one. Okay, so on the first, we'll say stage. And the photometry and spectroscopy. So also I should add the wavelength band. So the initial stage, this thermonuclear runaway. The answer is for that, you don't see it. That's something which, so I'll say thermonuclear runaway. This is the initiating stage. What you'll see in the photometry is whatever the system was. That is, you'll see something that looks like a cataclysmic. So you'll see it flickering, you'll see the effect of the disk. It won't look unusual, not in that initial period. Spectroscopically, it's going to look like an accreting binary. And in fact, the general name for these systems is either old Novae or old Nova-like. You have to love these names. Spectroscopically, the only place you'll see some signature of something possibly happening is in gamma ray or in X-ray, specifically in gamma, when the explosion has just begun and you're seeing the initial fireball. The fireball stage, this will be in the photometry, a rapid rise that is no more for in general, for a classical nova than days. It may even be hours, but this is where you'll see a change in the visual magnitude of perhaps 8 magnitudes or more. Now, what you're seeing, I should explain, is in this stage, as the ejecta are expanding. So we'll just use a slice out of it. This region has a temperature that rapidly drops on the expansion. The fireball is going into nothing, just free space. And like the expansion of the nuclear fireball, it goes thin, but it doesn't turn really transparent. The temperature drops. And the peculiarity is that in dropping, it suddenly becomes more opaque instead of more transparent. It's only hydrogen that becomes more transparent as it cools. But metals turn just the opposite. The neutrals are much more opaque than the ions are. And so you get something that has a peak that's originally in the UV that suddenly shifts into the visible, redistributes the energy, and that's what you see as the peak. At that point, the low resolution spectra will look like an A or an F supergiant photosphere. You won't be able to tell just from looking at the kind of general spectrum that what you're seeing is an expanding fireball. It'll look at low resolution just the same as a supergiant because the physical conditions, the temperature and the density and the pressure are just about the same. Never mind that the thing is expanding freely into space. At that moment, you're just seeing a portion of it. So you're seeing what looks like an atmosphere sitting on top of something which, although it's cooling, is cooling more slowly than this region is dynamically adjusting. Then, so this is what you'll see in the optical. So in the UBV, for example. The next stage is when this has turned so transparent that now, instead of being just a small fraction of the volume, it's the bulk of the volume. And so the optically thick surface is here, still the fireball. And the rest of this stuff is transparent. So you're sitting out here, you're seeing the emission lines from this gas, and maybe you're seeing some absorption in this line of sight, maybe. So the line that you see is going to be virtually all in emission, where this is in velocity, but there'll be maybe a little bit of absorption in here. And then eventually this material will have expanded so far. So this will be a sort of, so then we get to the pseudo P Cygni, so-called. That is, you'll see emission lines. And the emission lines are going to be from helium, iron, everybody's favorite, hydrogen, so on. The photometry is going to turn progressively more uninteresting. That is, it's going to get to the stage of dominance by the emission lines and not just by the underlying object. Okay, that's very important. Photometry is virtually useless in the later stages unless we actually can see the white dwarf. So once the ejecta are only in emission, then in the, let's call it early decline. So there you would have the expanding ejecta. The photometry is going to be pretty much a combination of the system input and some of the ejecta. There's only one thing that can really dramatically change this. If the ejecta were massive enough, it can form dust. That is, the temperature can get low enough. And by processes we still don't understand very well, there's still debate about which mechanism triggers the dust formation. We know it's dust. We know it's really dust because it's polarized light and it emits in the infrared, and the temperatures are less than 1,000 degrees equivalent. But exactly why it forms, when it forms, we don't know. And the key is, this is at about 160, excuse me, typically 60 to 100 days. Remember I said there's this characteristic brightness and the characteristic rise in these systems. This timescale also is kind of sloppy. It can be as short as 40 days or as long as 150 days. Doesn't really matter. The point is, long into the free expansion, when the explosion's over and this is just cooling ejecta, expanding outward, suddenly the bottom can drop out of the light curve. At that point, things get interesting for the photometrist. What you see optically, what you see in low resolution lines, I can show you some models of in a few minutes. But that last stage, so if the dust curtain forms, which is usually done on analogy with DQ Hercules, which was the first one to do this, the so-called deep minima. Then in the photometry, you're going to see a sharp drop and slow recovery. And almost no change in color. It's a very important indication that the dust is very large. At this point, you're already looking at a system that's very blue, but it simply loses light. And in the optical, in the low resolution spectra, that's a question I can't answer. It's very, very sensitive in predicting what you'll see. The lines will suddenly turn asymmetric, that I can tell you. But how well you'll see that depends on your resolution. And that can last for a long time. In fact, here, rather than just answering it, let's see if I can show you an example here. So here, I hope you can see this. On the top left is a model for, I just did these a couple of weeks ago. This is the result of modeling the ejecta using the ideas that I was telling you. The ejecta predicted would look like this if you could stand next to them. This is an emission line. The velocity range is a couple of 1,000 kilometers per second. And
we don't.
Steve, we only see drawing, and there's a couple of questions for you.
You can't see the screen?
No, we can see your screen, but that's only the drawing you made.
Ew. So let's try it this way. Okay, here.
We can see the mouse. Yeah, now we can see the. Yep.
Okay.
The PowerPoint. Yep.
Okay, so just to make this fast,
Yep.
if you take the equivalent of this fireworks and you predict what the ejecta would look like, okay, this is what this ejecta produces as a line profile. So if the maximum velocity is like 2,500 kilometers per second, this is what the ejecta will eventually give you. And this is very much like what Novae 2013 looks like. But if this starts to form dust and the dust forms on the outside, then the profile, which has now gone to something like this, as this is expanded, suddenly turns asymmetric. That is, the red side, which is, let's say, from here and you're down here, all of this is absorbed locally and in passing through the other side of the ejecta. So you lose the red side preferentially to the blue side. That's the signal of dust formation. Okay? That is the observation.
Yeah.
That's Novae.
Oh, great. Steve, to follow up on the drawing you just made, is it possible to make some kind of general timeline for the stages?
No. That's the key. That the energetics are not so uniform that you can do that. And more to the point, and this is something that's currently, if you'll allow me a polemic, making me very angry in the way things are being reported. When work on Novae, when new observations are reported in, say, the Astronomer's Telegram, or making the rounds on the AAVSO or the like, the terms iron 2 Novae and helium nitrogen Novae are being thrown around. Those are meaningless. And that's why I can't tell you one time scale. The problem is fundamental. We know the ejecta are not spherical. And because of that, you get different evolutionary times just by looking to the side or down the pipe, so to speak.
Yeah.
If you've got the ejecta expanding this way, you notice my hand is optically thick, okay? You can't see my face, but now you can. You're still gonna see my hands, okay? These are still gonna be emitting, but in this case, it looks like it's completely covered, and so you'd see absorption. In this case, you'd see emission. It's the same thing seen from the side, okay? This is the danger that we have in astronomy, which pervades the field, that you use something that's descriptive, you create a classification, and you don't ask yourself, does this make physical sense? The answer is it doesn't. That if you have the nova this way, it evolves photometrically more slowly than this way. It's that simple. So a fast nova could very easily be one that goes like that, okay? Where a slow nova could be one that goes like that.
Okay, that makes sense. We have another question.
Models are easy, by the way. You can do these in your head.
We have another question about time, so let me take that. Approximately how long time lasts from one nova to another? Is there some kind of rules it follows?
Okay, this is also connected with the great mystery. How do these things reset? The shortest time scale we now know is 1 year. It's one of the novae that recurs in Andromeda. It's got a telephone book-like name, but it's recurred now, I think, 5 or 6 times.
Okay.
And it actually is close to clockwork. In the galaxy, we don't have anything that fast that anybody's discovered yet. The one shortest in the LMC is about 6 years. That was first seen in 68, then again in 1991, and then it's repeated several times since then. So we know we missed a few. USCO is repetition time of about a decade. TPIX is supposed to be about 20 years, but it missed one. So by definition, to say that something recurs requires that it's got to have occurred within the last couple of 100 years for the first time, unless there's a damn good reason for thinking that you saw an outburst of one that must be a repeater, but nobody had seen the previous examples. I know one example of that. Other than that, there's a graveyard that the less massive systems, or the ones that are accreting at a lower rate, and that's determined by the binary, not just by the white dwarf. So this depends on the family you're born into, not just your own personal whims. These may recur on 10,000 year or so timescales. Between those two, there is an enormous gap that we haven't filled. There's no reason why it can't recur on anything from years to centuries. No physical reason impedes that. Except how long it takes after an explosion for the system to come back to quiescence. Since we don't know that, we don't know what resets the system. We know that in some, these very fast ones, those particular freaks reset almost immediately, but virtually none of the others do. I mean, we only know a couple, at most, a few dozen recurrent novae in the local group. We know thousands of novae, whether in the local group. Take the galaxy Andromeda and the Large Magellanic Cloud, just put those together, and we have more than enough to say, well, these others, the small group, they're really freaks. They're the same physics, the same explosion, but something happens that's different in the post-explosion system. I hope that answers the question.
I think that, Steve, should we continue with your explanation, or should we take another question?
I really love the questions.
Okay, this one is also of my interest. It's from Johan Fynbo. I wonder how important these objects are for the dust budget in the interstellar medium. Is it just a tiny source of dust, or is it significant to the overall dust production in the galaxy?
That's a really beautiful question. And the answer is, again, we're not quite sure. I think the simplest answer is no. We can trace them. We can use them in the same way that certain classes of pollutants can be used to pinpoint the source of pollution. But no, for one thing, the amount of mass that's thrown off in dust is very small. It's a small fraction of the total mass of the ejecta, which themselves are about 10 to the minus 6 or so solar masses to 10 to the minus 4. In other words, it's about the mass of a planetary system, which is nothing. But most of the dust in the galaxy that's been recycled is coming either from supernovae, where it can be solar masses of material that condenses, or in the much more likely and general source, the winds of extremely evolved stars. That in a wind, you have a chance to, well, it's like it acts like an air conditioner. You're blowing a wind out of a source. You're blowing it away literally as a continuous fan, and as it's expanding, you have a high density a high density flow, and somewhere in that flow it condenses out. So it forms dust. Again, the process is going to be a little bit more complicated than it is in the laboratory because it's taking place on hundreds of solar radii, but these sources can stay on for 10 to the 5 years. They can pump an enormous amount of mass back into the interstellar medium. The asymptotic giant branch stars, the things that become planetary nebulae, are the much more likely source. Novae, though, do leave a signature. Actually, here, just to make the point, they do leave a signature. This is a sample from the Washington University group that does astrochemistry on pre-solar grains, looking at evidence of grains that were not formed in or grew within the solar nebula. You look for things that have anomalous composition, tiny intrusions of micron size. And among those, you've got those that are coming from asymptotic giant branch stars, like, for example, these that have an enormous carbon 13 to carbon 12 ratio. This is where the sun is, right in the center. So this is what these ratios should be. But from the nuclear processing that occurs in red giants, you get carbon stars, and these have enormous excesses of carbon 13. And then down here, this little group called N, these are the novae. They're there, small percent, but when you consider that these are singular events that occurred in the history of the galaxy before the solar system was formed, I think it's rather impressive that you can find grains that have made their way across kiloparsecs of the galaxy. Okay, there weren't novae right next to the sun. There may have been asymptotic giant branch stars in our neighborhood, but these are too bloody rare. This isn't that somebody came along and did the equivalent of pouring something into the mix of the solar nebula, okay? This was stuff that had already been well mixed into the interstellar medium. These grains survived giga years.
Okay. I think that was the last question for now. So please continue if you want for a little while more, and then
okay.
I have...
Well, maybe one point to sort of direct to is the role that observers have in all of this. That there are a couple of things maybe I can add here. There's a tendency with transients to go for the quick kill. That while they're bright, you observe them, they're interesting, you get enthused about them, and then they become faint. And it becomes a little bit hard or very hard to follow them. And the problem is what I'm trying to explain here. Everything that we know about the moment when the ejecta were frozen is recorded in the ejecta. And so once that turns transparent, once it enters the so-called nebular phase, where it looks like a planetary nebula, in effect, with a weird velocity structure, at that point, you can go backwards and get information about the structure of the ejecta, the way that it was polluted. But you see that as a frozen record. You're doing archaeology at that point. The record was left for you. You cannot change that, and you can't run it forward. So you don't know, once that is thrown off of the star, you don't know from that what's happening on the star itself. You don't know what resets the system. And more than that, there are fundamental questions of interpretation here. I guess to show you one example, this is an observation that hasn't yet appeared in print, but it's coming out. This is Novae, 1 night's worth of VLT data. There are about 60 spectra stacked here. This is in radial velocity, and we're looking in this plot. I'm showing the helium-1 line at 7065, and this line is from the ejecta, so it's not changing. That's the profile. This line, the line that comes from permitted helium, is tracing the underlying binary. At this point, the ejecta could be separated from the underlying star. We didn't know the period. We determined it theoretically to be probably 3 to 4 hours, and the period turns out to be just about 3.66 hours. It's that we're seeing an accretion, a disk or garbage around the white dwarf and the companion being heated, and that's the part that I guess I should also explain. So you got the whiteboard again?
Yes, we have.
Okay, so this is sort of the last part of that table. That what happens after the explosion, we think, and you got to understand this is kind of a biased point of view, so don't take this as written in the proverbial stone tablets, but kind of written in silly putty, that you've got the white dwarf now much engorged relative to its normal size, which would be something like that in relative size. It's somewhere between 10 and 30 times larger than it should be. The companion is filling its Roche surface, and it's very low mass. And this is surrounded by junk, some of which is condensed because you've got the stream still coming out, some of which is being heated by collisions. And all of this is also having this front face heated. So as the system orbits, you see this part giving you that S-shaped wave. And then around the white dwarf, there's also this hot spot. And so here, if this is time and this is velocity, you get this as the curve for, we'll call this L1. You get this as the curve for the hot spot. And that gives you this behavior. Okay? We can then trace, and you could do this. You can do this in low resolution. This is 500 kilometers per second from this side to this side. You can do this for different lines. Here, this is just an ensemble showing, this is one night's observations. We did 2 nights on VLT separated by a couple of weeks, but this is like 8 hours sitting on one object. This is only ejecta. It's not varying at all. And then each one of these is tracing something different about the system. On the left is the model, just the prediction of what would be, the cartoon I just drew for you would be like. And that was done before we did this. So again, this is just a way of saying at this point, we know the geometry of the system, but we don't know what got it there. Here, We know that this stuff is unincorporated. The dwarf is still bloated. It may even have some residual nuclear reactions going on in its envelope. We don't know that. So photometrically, and eventually with other telescopes spectroscopically, you got to follow this. Now, it may be that this happens quickly. By quickly, this will probably be over in a matter of a decade. But whether the disk has reestablished, whether the accretion is now quiet, whether all the material is getting onto the stars, some of it is getting blown out of the system, we don't know. And there's a reason for worrying about that. It changes the way the stuff mixes. It's exactly the same as that example I used of a carburetor, in that you're taking the gas and air and you're pre-mixing it before it goes into the spark. It makes a big difference if you try to put a spark to gasoline that has no air mixed into it, okay? Or air that has virtually no gasoline mixed into it, right? It's the same thing here. The triggering is going to depend on the degree of mixing. There's another reason why people like me get fascinated by this. It's not just for the Novae. This is what happens when stars turn on their nuclear processing. It's just happening faster. So we've got this possibility here of probing the physics of something we will never be able to see directly. I don't mean we don't have the instruments now. I mean nature obscures it fundamentally. So here we've got the chance, maybe not absolutely directly at literally the moment, but here we have the chance to understand the way that a thermonuclear process initiates, the way it burns through, what the dynamical reaction of the background is, and then we can put that information into our understanding of stellar evolution. That's another reason why these objects are important. You know, as such, people who make their careers studying particular classes of objects can be, I think, remarkably content at the end when they say they've understood something. But I sometimes wonder if we don't lose something of the beauty of what we're doing as astronomers by focusing on the expertise in the diversity instead of seeing the unity of these things. It's the same basic physics playing out in different environments, that you can either try to understand every single environment, or you can start seeing how things become lumped together in common. I hope that that's making sense. To make a personal statement, my reason for doing astrophysics is because I don't want to be an expert. That I hope it's the same reason for you. It's not just the wonder at these things, it's the fact that the bloody universe fits together. And there's something amazing that you can dissect these individual pieces, but then you start putting them back together and you get the universe. You can't do it in a reductive way. You have to understand the diversity of the environments in which the same physical processes manifest themselves. It's not the other way around. These are not laboratories. We can't control this. It's very much coming on the corpse and trying to figure out who the murderer is, but using the basic laws of physics and chemistry to understand how the corpse got into the state you find it in. You know, here, the processes individually are actually relatively simple. It's the manifestation in each one of these settings that's so different. If you keep that in mind, you'll be able to see past the diversity and toward this kind of unification. And maybe that's the other point about the table, that the stages are manifestations of particular physical transitions that are occurring inevitably in these conditions. You can actually do this stuff in your head at the beginning. The quantitative comes later, but understanding what would happen if you take a sphere with some finite mass, blow it off, have the source inside, stay active, and ask from the outside, what are you going to see as this expands? You can actually do that from first principles. And then you can say, well, if it's slow, we call it a planetary nebula. But yeah, not quite. If it's fast, we call it a nova. If it's, and you can extend this.
Yeah. Okay.
Well, at this point, there's still something that, a lot of things about that little bugger. I have to say, I don't understand yet, but I haven't had the chance to go really thoroughly through all of the Aris spectra. But for the time being, I'll say that the phenomenology is clearly that of a not completely filled shell. So something that kind of fits this picture. Maybe I can, here, this is pretty damn close to what I think you're seeing, that we're still looking sort of in this direction. And the helium and other emission lines are, the fact that it looks like an A star just means it's still optically thick. That the portion of the ejecta here that lies above this sort of photosphere is still relatively compact and comparatively cool. Now, it is entirely possible that Cass is another one of these that we're starting to think of as imposters, things that show the phenomenology of novae, but maybe are coming from very low mass objects, that they're kind of failed thermonuclear runaways. But I'm not sure. The only thing you can say easily for this is it's relatively low velocity, that it shows the helium lines, just tells you that there's gas with a temperature of maybe 20 or 25,000 Kelvin, that is showing the emission lines of helium without showing the emission lines of iron is no big deal. That it went from an iron type to a helium type is no big deal. That just means a change in the optical depth. You know, all of these individual changes don't mean when it's not spherical, when it's highly structured, like filamented, you get these transitions. Those are the individual peculiar behaviors. Dell was basically the same thing. It just happened to have been a more regular nova. Sen was very much the same thing, but one that we just studied last year, I think. Yeah, last year. Assassin 17HX is one of these that we think is looking like a nova. It was classified as a very slow nova, but it's an explosion, but it's slower. To do more than that would start to get like, I'm probably a little heavy, but the explosion happens more slowly on low mass objects, although the lower limit is something that we still don't know for the mass that will in fact blow up. But there are white dwarfs in symbiotic stars that can go into a thermonuclear runaway that fizzles. It doesn't go to an explosion. It just gives you an engorged white dwarf. And those can last for decades. These are real explosions. I mean, it's clear that material was explosively ejected in the Cass event, but there are a lot of similarities between that and H.R. Dell, 1967, and other slow novae. So my guess is it's on the low mass side, not spherical, and probably seen at a moderate angle, and all the rest of the phenomenology is very similar to, but not sequential as some of the other novae you know.
There's another question here. It's about the new instruments that we are getting. Do you expect that ELT telescope or the JWST will contribute to deeper insight into Novae?
I'm going to be a little heretical here. I don't think JWST is going to have a damn thing to do with this stuff.
Oh.
You see, there's a problem when you have a fly, it can turn very quickly, and when you have an elephant, it can't. And when that elephant is at a Lagrangian point, it takes a long time to figure out where to point. Novae, for one thing, aren't important enough in the long run. I say that as somebody who's devoted a lot of time to thinking about these things. They're very important in some of the physics they reveal, but they're not so important that they take precedence over the limited resources of the space telescope for the most part. Now, we're currently writing a proposal to look at Nova Sen one last time in the ultraviolet, but that's in the UV, and that's late. The early stuff, we got the only sequence that's likely ever again going to be obtained in the ultraviolet. JWST is an infrared instrument. We can do most of the important things from the ground in the infrared for these systems. We don't need space observations. For supernovae, it's a different issue because those can be at large redshift. And so there you definitely need the time-dependent coverage. VLT we used, and the spectra I showed you of the binary at the end of Nova Sen, that was VLT on 2 nights. But it took a lot of work to get the committees to think that it was worth giving us 2 nights on VLT. The VLA is very important, and SCA is certainly going to be. My suspicion is that once LOFAR really has its act together for looking for transients, it's going to be very important. ALMA has yet to be used on these, but I am certain the observations will be astonishing when we can actually do this stuff in detail in the millimeter. VLT is being used now also for the imaging of the ejecta, and I think that's where the greatest contribution is going to come in. ELT may be useful, but not for the outbursts. That can be done now so effectively with CCDs on small telescopes. The real problem is more the lack of the small telescopes. No, it's not too small. If you can go down to 14th or 15th magnitude, you can follow any naked eye nova practically to quiescence. Okay, these things only have amplitudes of 10. So if you have something that can get you down to 15 or 16 in photometry, and many can get down below that, there's no problem. For spectroscopy, for low resolution spectroscopy, yeah, that may be a little bit hard, but that's when you go to the bigger telescopes. I think the biggest problem we have now is that with very few exceptions, like the Liverpool, most available telescopes that can work in a target of opportunity mode don't have spectroscopy, and they're too damn small. Master and Ogle are not 2-meter type telescopes. Liverpool is, and it can be operated remotely. Tigre in Mexico can be operated remotely, and that has a very good spectrograph on it. But there are very few. There's a network that Blundell has organized for following SS-433 and other jet sources. And that's got a spectrograph on it now, but I don't really know how well they know how to use them for that. So they're pretty much sticking with their original programs.
Okay. Johan Fynbo provided us with some historical data from the Novae Hercules in, it was
1934.
Yeah. And I will share my screen and then I can show you it. Just a second.
Okay.
I think this is interesting. I don't know any historical. I think it's very interesting. So here it is. Can you see it?
Oh, yes. Yes. Well, it's just formed dust.
Yeah.
Kind of dark.
Yeah. From what I can see from Johan, it was, I have to scroll back. It's from just a second.
Sure.
Here it is. Can you see it now?
Yes. Now, let me ask, okay, this is from...
It's from a Danish amateur astronomer, Arthur Nielsen, who observed it called Fredericia.
It's just a small part of it. He had 10 years, so it has a 10-year-long sequence of the.
Oh,
that is...
Please fill in, Johan.
So I have the whole sequence over 10 years. So this is just the beginning where it had the dust dip and then it just goes on.
The thing that you notice is somebody decided that they were going to draw certain lines here. And so a lot of the structure before the dip that's real, because I'm sure that looking at the scatter and some of the points, Nielsen was able to do the
Indeed, right?
Okay, but you see the stuff before the dip, like near the maximum.
Yeah.
So he caught the fluctuations, but didn't realize their significance. So he just drew a line.
That's my mistake, because it's me drawing the line. It was a high school project. So it's me who flunked, not the observer.
It's your work, Johan.
The remarkable thing about this is how easily it was interpreted. That even though you had no idea even that novae were binary systems, you had no idea that they were explosions, that this was dust was the immediate response in the 30s, because the R-core Bohr stars that do the same thing, except they do them repeatedly. These are highly evolved supergiants that go through dust forming episodes as they blow material off in their winds, do exactly what these novae do. So if we understand how novae do it in these single events, we're going to be able to transfer that. But the remarkable thing about this curve is how similar it is to all of the others that go through this stuff, these deep dips. That in that sense, there's something self-similar about these, which means the formation process for the dust must be very similar from one of these events to the other.
Yeah, there's another one here from
That's beautiful.
He sent me here. I have to stop. There's something annotate. I'll just do like this. Just a second.
Actually, there's another thing historical, Lars, that Stratton produced an atlas based on the combination of plates, like 600 plates from all of the observatories that were working on this nova at the time and produced a photographic atlas 1 day at a time of the spectra. The photographic plates were reproduced. And you can actually find that on ABE Books and Amazon as a used book. Francois Tessier and others have tried the trick of scanning of making PDFs from the photographic image and then seeing if you could extract the low resolution spectra, and it works.
Amazing.
So you can actually go backwards to these 1934, 1935 plates. This nova before, I think you could say before Novae, this was the most extensively covered event spectroscopically that I know. And Dell surpassed the wildest expectations. That the overall contribution to that was more than a joy.
Yeah.
I mean, the story behind that, I think you know that we had a meeting in Pisa in July 2013 to just a small group. It was less than a dozen of us who were going to decide how we would fill the gap in our knowledge of the nova event, spectroscopically, photometrically, in X-rays and gammas. We had everybody there. It was kind of a summit meeting to say, okay, let's do a legacy. If the next bright nova goes off, let's do it right, coordinate everything, and produce something that the community will have as a permanent record, with DQ Her sort of in the back of our heads. And 1 month later, happened Novae, and everything was planned. We had a proposal into HST, already submitted and approved. We had observations with SWIFT, with Chandra, with XMM. There were radio observations, and then you guys jumped in, and the amateur community was just astonishing. I mean, it was the most, it was one of those events that, at least for me, changed my life. So I have to thank all of you, even just for the enthusiasm and interest, because it meant that something that would otherwise have just been a curiosity became real, an international effort to understand physics. A real effort. I mean, not this crap of pro-am or anything like that. It was just science, period. In the best way, I think.
Yeah. I feel the same.
Thank you, Doc.
Thank you.
Thank you,
Steve.
Thank you.
Thank you very much.
Thank you all. From the bottom of my heart, thank you.
Okay, mange tak til jer alle sammen, fordi I deltog og havde virkelig god mødedisciplin.